SCWD webinar. Welcome back. We're excited to continue our webinar series to highlight a broad range of water issues, programs, and projects impacting our region and the industry at large. Before we begin, I do want to mention that we are in webinar mode, so attendees are muted to reduce background noise. The webinar is being recorded and will be available on OCWD's website and YouTube channel. Lastly, we'll take questions at the end of our presentation, so we do encourage you to submit your questions in the Q&A box located at the bottom of your screen, and we'll do our best to get to as many questions today as possible and address questions most relevant to the information presented today. In the event that we're not able to get to your question live during the webinar, we are happy to follow up with you after, so please do include your contact information so we could follow up accordingly. Let's see. So today we're doing things a little different as we welcome Rob Thompson, General Manager of the Orange County Sanitation District, as our special guest speaker to talk about things from the wastewater perspective. So for decades, our agencies have partnered to advance water and wastewater issues respectively with projects like the groundwater replenishment system. For those who don't know, the groundwater replenishment system is a joint project between both our agencies, and it's the world's largest water recycling facility, which now can take 100% of OC Sound's reclaimable wastewater flows and produces 130 million gallons of water every day. Our agencies are also on the forefront of addressing issues like PFAS through increased lab testing, researching effective treatment options, and finding ways to remove PFAS in water and wastewater, respectively. At OCWD, our program is focused on removing PFAS detected in the Orange County groundwater basin. Our efforts have brought back more than 30 impacted wells, and we're continuing to make significant progress to build more treatment plants and wells and bring more impacted wells back online. And for OC San, we'll hear about their Supercritical Water Oxidation project. This pilot project will address the need to treat PFAS and other contaminants of emerging concern in biosolids and advances OC San's objectives to investigate new technologies to protect public health and the environment by providing effective wastewater collection, treatment, and recycling. So without further ado, I'd like to welcome Rob Thompson, and I know you're going to share your screen, so I'll let you take it from here.
Thank you very much. It is always a pleasure to be with you at the Water District, our valued partner for many, many years. So we're all set. Everybody can see my screen?
Yep.
I'll go with a yes. Excellent. So what we're going to talk about today, I want to make sure you understand who OC San is, what we're up to, and where we're going. Very busy time for us. But first, OC San, as most of you are probably aware, serves 2.6 million people in north central Orange County. We have generally the same footprint as Orange County Water District. So that makes our partnership very easy from that perspective. We serve the same people, and we both agencies look at the ratepayers as one group. And we're doing our best to make sure we maximize all the resources, all the assets that we've built together for maximum benefit. And I'm going to talk about what some of those benefits are in just a second. But in general, we collect about 180 million gallons per day from 479 square miles. We service the 20 cities you see here, 4 special districts, which are Irvine Ranch Water District, Costa Mesa Sanitary District, Midway City Sanitary District, and Yorba Linda Water District. We have 388 miles of sewer. These are generally going to be the bigger pipes, anywhere from 18 inches all the way up to 10 feet in diameter. We have the 2 treatment plants here in Fountain Valley and in Huntington Beach. And something that we probably don't talk enough about, one of the most important assets in Orange County, our outfall, which is a 5-mile long outfall, which allows us to make sure that brine that we're now making from all the reclaimed water is safely discharged and maximizes our ability to reuse the water. Again, a little bit closer view of our facilities. On the extreme left, you will see our new headworks area. This is the nighttime rendering. It is nearing completion. For those of you that get a chance, probably in the summer, good time to stop by and see the new building. It's a mass timber structure. It's going to be beautiful and very, very effective. We saved quite a bit of money with the mass timber construction, actually. It's much lighter than concrete and steel, so we saved significantly in soil preparation and foundations. So both beautiful, warm, and efficient. But the heart of what we do are treatment plants. As many of you already know, our Fountain Valley plant is here shown bound in yellow, and the Orange County Water District is right here co-located. We share a campus. That's part of our cooperative nature together. Plant 2 in Huntington Beach is right here. It's about the same size, different shape as Plant 1. They're both about 100, 110 acres. Both treat about 320 million gallons of wet weather flow for a total, if you do your math right, 640 MGD. And our 2 outfalls can handle that, along with our 3rd outfall, which is the groundwater replenishment system. So our first job, what we started as an agency doing in 1954, and really as a joint outfall sewer agency from the 1920s, was protecting the public health. That is job 1 for us. We make sure all of that biohazard, all of that sewage stays out of the streets, stays out of the rivers, gets to our plants, gets treated, and safely discharged. Now, over time in the 1960s, environmental movement kicked in, Clean Water Act. We expanded to becoming protecting the public health and the environment, something we take very, very seriously. We have been providing Class A beaches for years. I've been here 28 and a half years. Since the 1990s, we've had A ratings on our beaches, really past the 2000s. Beyond public health and the environment, we're now really moving into maximizing water reclamation and resource recovery in general. But water reclamation, as you heard, our partner, the Orange County Water District, we work hand in glove together. All the water that we collect, we're working hard to make sure it's reclaimable and made available to OCWD. We work hard to make sure we're a good partner, meaning the water quality we provide them is consistent. It matches their needs when they're running their membrane filters and the different flavors they have. Our consistent effluent is the key to them having good success running those filters. So we take a lot of time and effort to do that. And it is the largest plant of its kind in the world, and we're happy to be involved. You can see the pictures of the general managers over time that really made the thing work. In addition, OC San has been collecting urban runoff since about 2000. So we're heading toward 25 years here, where we have been diverting dry weather urban runoff into the sewer system. We did that initially as an environmental program. Our job was to make sure the beaches were grade A quality. As I said, some new monitoring requirements went in place in the 1990s, and more sensitive testing means you find more things. We went through the work of identifying what was causing beach contamination. Initially, everyone said, oh, if it's contaminated, obviously it's coming from the sewer plant. After 2 or 3 years of exhaustive study, it became clear it wasn't OC San. We knew it all along, but we had to prove it. It became clear that it was urban runoff, those storm drains dumping that urban slobber, as we like to call it, into the ocean. We worked hard with our partners, principally the county, Huntington Beach, and Newport Beach. Later on, we expanded with Irvine Ranch Water District. We collect up to 10 million gallons a day for free. Right now, that number on a regular day is a little less than 2 million gallons a day. It is growing. Connections are being added. 6 MGD of that capacity has been subscribed. So it's a very popular program. We accept that water for free. The upside now is the water coming to the plants is also reclaimable. So it's now a triple win. So again, looking for those innovative opportunities to make things better for the county we serve. So all of this stuff is happening. We are getting more concentrated wastewater over time. Testing methodologies are improving. We're accepting water from urban runoff. So it's got things in it that are contaminants or constituents of emerging concern. These are the things that are sort of top of mind in the industry and becoming more prevalent in day-to-day media. OC San, as a function of its operations, makes more than 500 tons of biosolids every day. Biosolids are the solids that we collect, either sludge from primary treatment or secondary treatment, or scum, which is stuff that floats. All of that is collected. It's put in anaerobic digesters. They're stabilized, so the transition from sludge to reusable biosolids is at least 15 days. We average about 22, 23 days in a digester at elevated temperature. We lose more than half of our total solids. We volatilize them, turn them into gas via the biologic action. We turn that gas into electricity and heat, which serves not only the buildings that we have here, but the process. So our digesters are heated with that excess heat from our engines every single day. Very effective, very efficient, but in the same way, regulations have moved through the 70s, 80s, 90s, and 2000s. They continue to move. We see a lot of pressure on this agency and the industry with biosolids reuse. There's a lot of noise right now about lawsuits, especially in the last week or so in Texas, with PFAS contamination of biosolids. We anticipate there will be more and more difficulty being able to beneficially reuse those biosolids over time. So OC San is committed to finding a way forward that may be different than how it has been over the last 50 to 70 years of our digester use. It's not just PFAS. There's also microplastics, which I think are as big a problem in the lexicon. So the concern about dumping PFAS, and a farmer might say dumping, having PFAS or microplastics end up in a farm field, as well as pharmaceuticals or whatever comes next. Our job is to make sure going forward, we have a way to deal with the wastes that we receive and find a way to turn them into some sort of beneficial nutrient or energy or something. Just for the record, I think methane production is also going to be under more and more pressure. It is a greenhouse gas. Southern California Gas Company and others are doing a lot of work looking to go to hydrogen and some other versions of methane through using renewable energy like excess wind capacity or photovoltaic cells to convert methane to hydrogen. So long term, I think we're going to have to rethink our model as an industry, and certainly OC San is thinking in these terms now. What do we do in the future if anaerobic digestion and biosolids reuse really come under even more pressure? So that's really what I'm here to talk about today. First thing we try to do is source control. We have a fantastic source control program. The best way to have something not in the wastewater stream is to never let it in the first place. So our source control folks are always sampling. When we find a constituent of concern that's high, out of the normal bounds, they're great sleuths. They do their sewer detective work, and they work really hard to identify where it's coming from and then work with the dischargers to make sure that that's limited. It's something that we really kicked up over time when we started GWRs, especially because we understand that their work is not only for ocean protection now, it's a function of public health, making sure the water we drink is safe. However, there are certain things that no matter how hard we try, they're going to come into the sewer, and we need a paradigm shift. I think everyone in this industry has kind of grown up from the 1960s forward, hearing the old slogan, the solution to pollution is dilution. Well, I am here to challenge that tried and true notion and say that the solution to pollution is definitely not dilution. I think going forward, the solution to pollution is concentration and destruction. So our job, I think, going forward is going to be to find ways to concentrate whatever these constituents of emerging concern are, these health hazards that have been identified or are concerns, and destroy them. We can't just stay in the business of moving them around. So taking PFAS, putting it in some sort of media, and then sending it away. The point is, I think the industry is going to come to the conclusion that there is no away. For us, biosolids tend to be one of those sticky substances that microplastics and PFAS stick to. We see some concentration there. So that's why OC San in our work program is looking for a way to take care of that concentration of either microplastics, pharmaceuticals, and or PFAS, and destroy them. So how are we going to do that? I'm so glad you asked. We have been tracking as an agency, and me personally, a interesting property of water, which leads to a subset of technology, which is called supercritical water. So water and carbon dioxide are two weird compounds in the scheme of things. They are unique in that they have a fourth phase. We all went to high school, had that basic science class where you learned water can be ice when it's cold. It can be water that you swim in, and if you heat it up to boiling, it'll turn into water vapor. Those are the three phases of water. Well, voila, if you go to a two-dimensional graph and move off your 1 atmosphere line, you will see that there are actually 4 types of water. There's ice, there's liquid water, there's water vapor or steam, and there's supercritical water. What's interesting is supercritical water is unique in its properties. So as long as we're busting prior views of the world, we all know, we have all been told forever that water and oil don't mix. And that's not true for supercritical water. We were also taught in high school that water is the universal solvent. That's not true for supercritical water. So while oil and water mix, salts are no longer soluble. So it changes your opportunities. It changes the way you can manipulate process flows and do some pretty unique things. And that's what we're going to try and take advantage of, that process. So for the science geeks, I'm going to take a minute. For those of you that aren't scientifically inclined, do your best. I'll try and use easy terms. But if you take sludge or biosolids or food waste, any organic matter, and you have it at room temperature, you're pretty much 1 atmosphere, 20 something degrees Celsius. What I'm going to show you is a machine that will pressurize that water laced with organics. Then we'll heat it up at pressure. We'll go into the supercritical phase, react it with some air, cool it back down, and then drop the pressure out of it. What's interesting about that, and what's really important, one of the problems we've always faced with trying to turn sewer sludge into energy is you have to dry it to burn it. It takes a lot of energy to cross this line and this line, like 16 times or 32 times, and I had that backwards, 16 times the energy to cross this line and 32 times to cross that line. That's why it takes ice so long to melt in your glass of water. That's why it takes so long for water to boil. It'll get to boiling, but it takes a long time to turn it from liquid to steam. The upside is it doesn't have a penalty to cross this line. So it's very, very efficient to move back and forth between high pressure water, and supercritical water. So the machine we're going to trial looks something like this. First step is you have an air compressor. The air compressor, very standard. Yes, it's high pressure, but it's not exotic. It's not very difficult to find an industrial compressor that can go up to 3,400 pounds per square inch. In fact, if you go to Home Depot and go to the aisle where the pressure washers are, it costs you a couple $100 to buy a 4,000 PSI pressure washer. So we compress some air. We put it through a heat exchanger where we're going to take heat that we've created by oxidizing the sludge or organics that we're talking about. So this is free heat. You end up with this hot pressurized airflow that goes to this point. Separately, there are some pumps that pressurize the organic, either biosolids or raw sludge or food waste in our case. Take that sludge. It's still relatively cool, no big deal. We like that because sludge is super complicated, and trying to heat up sludge over time will turn it into tar and get you into problems with viscosities and how it moves. So suffice it to say, compressing sludge, no big deal. I do that every day. I take my biosolids, put them in a concrete pump just to pump them to my truck loading facilities, as many of you know. So a few thousand PSI for wet sludge, not a difficult proposition. I run it through this heat exchanger just to heat it up some, not super hot, less than boiling, but just to kind of preheat the sludge. It's free heat. Hot air, pressurized sludge meet, and go into the reactor. In our case, the reactor is very complicated. I'm kidding. It's really just a piece of pipe. And in that piece of pipe, the air and the pressurized supercritical water and organics mix. Wherever that oxygen in the air touches an organic at that temperature and pressure, it oxidizes, and you create carbon dioxide, you create water, products similar to combustion, but without burning. It's just oxidation. So that hot gas mixture will come through with some salts in it. That's where the heat comes for the air on the way in. We dump it in a vessel. We allow the pressure to separate off. Our unit won't have an expander. The next unit we try, when we're successful at 30 tons per day, will have an energy recovery device. But we'll let that air and steam escape, and the water will come through with some salts in it that I'll talk about in a second. That's where the heat comes to heat up our sludge. And then we end up with a water mineral mix. So that's how the machine works. I know it took a lot to say it, but it's really, in the end analysis, pretty simple. Air compressor, sludge compressor, expander. Those are the big moving parts. The question is, well, what happened to all those nasty things that might have been in the sludge? You had PFAS, what happened to it is a big question I'm asked. So if you take PFAS and you run it through this, you will end up with CO2, because PFAS is really a carbon fluoride chain. The carbons will break apart, combine with the oxygens, you'll get CO2. The fluorides will break off, and you'll get calcium fluoride. So calcium, very prevalent in the mix. For the real chemistry geeks in the crowd, if you think about your periodic table, all those 2 columns, 3 columns to the left side of that periodic table, your alkali and alkali earth metals on one side are going to combine with your metals and halogens on the opposite side of the chart to make a bunch of salts. So as you look down this chart for products, you'll see a lot of salts, for phosphates, for sulfur compounds, for fluoride compounds. You'll also have nitrogen gas coming off. So the process is very efficient at breaking up ammonias, very efficient at breaking up fluorine compounds, PFASs. pharmaceuticals. This machine just sees them as fuel. Microplastics, no big deal. That's just carbon hydrogen bands. So you'll end up with carbon dioxide and water. So you end up with a pretty clean water compound with some salts sitting on the bottom of the beaker. So what's our machine physically look like? The machine is being constructed, and it's actually constructed, being tested in Indiana right now. So this first set of views is the sludge preconditioning. Sludge is an incredibly difficult media to work with. Even in today's world, we spend an inordinate amount of time working on our solid systems, whether it's centrifuges, digesters, truck loading systems. It's a very gritty, difficult to handle material. So we spent a lot of time making sure that our system would be able to handle the contaminants that we're dealing with. There's all sorts of, use your imagination, latex products, sand, pebbles, grit. It's a very difficult medium to work with. So the first thing we do is grind everything. There's a macerator in the corner. After everything is all ground up, we put it through a screener. So the sludge will come through. There's a fine screen. It'll let through anything less than about 2 millimeters. Anything bigger than 2 millimeters falls in this diaper genie. Or if you're a purist, it's an endless bagging unit, but I prefer diaper genie. Keeps the odors down. The sludge then passes through to this holding tank. Then we go to a screen press. We compress the sludge up to about 16% solids. So it's 16% solids, 84% water. And then we ship it over to our second container, which is where the magic happens. So this loop right here is our reactor. It's a very complex piece of equipment, which is basically a pipe going around in a circle. These items on the side are those heat exchangers that I was talking about. They're basically pipes within pipes, very efficient, straight pieces, prevents a lot of plugging issues. Very simple layout, very simple idea to get done, where 374 Water is really providing their know-how is in how it's all controlled, the geometry of how things are put together and mixed. A lot of work has been done. They've learned a lot in the past year and a half in how to build the machine to run effectively and efficiently. And I am here to say that I'm very pleased with how this is going forward. And we expect to see the outcome very soon, which I'll show you in a minute. The output looks something like this. This is the actual output of the unit right here. So the water's coming out. This was a video clip, but you can see that sandy, salty material down here at the bottom of the sink. This is they caught a cup of it. So it's water with these floating salts and precipitates. It looks very rusty because West Lafayette, Indiana, which is supplying the feedstock for them to test with, is similar to OC San in that it uses a lot of ferric chloride for enhanced primary recovery. Works great for us from a process perspective and just becomes a nutrient in the salts that are left. So this salty stuff that will be able to settle out, we think, pretty readily, will be high in potassium, it'll be high in phosphates, it'll be high in iron. So there's no reason to believe it won't be a pretty good fertilizer. It'll be totally devoid of anything alive because at 3,400 pounds per square inch and 750 degrees Fahrenheit, not too many biological things will last. So it's a great outcome for us. This handsome gentleman you see here with his hand in front of what feels like a dryer vent, this is the warm, moist air coming out of that expander area. So does it work? Yes, it works. This is a couple of beakers. This is what went in. This was the original SCWO testing at Duke University on the original 1-ton unit. So OC San sludge, I think this is actually biosolid, so it's even better than sludge. This is OC San biosolids, and this is the effluent water that came out. We had to do AQMD testing because South Coast Air Quality Management District wanted to make sure that what we were doing just didn't put PFAS into the air. They wanted to verify destruction, and they wanted to verify that what was coming out was safe. So we looked at NOx and SOx and all the things there, and got very, very promising data. We submitted that with our application and received our permit. They have run this same technology, this 1-ton unit. They've run pure AFFF through it as part of their testing. AFFF is the firefighting foam that has PFAS in parts per thousand, and they saw a 99.9999 reduction. So very positive results. Those are all ASCE paper certified. So we're very, very bullish that this is an opportunity for us if we can make this work with 374 water. It's a solution to microplastics. It's a solution to PFAS. It's a solution to pharmaceutical products. This is a way for us to morph away from digestion, maybe in the long term completely, or to augment digestion. We're still figuring out what the right way to utilize this technology is for OC San. But the upside is it solves a lot of the problems we may be facing in the future. So we're very, very interested to see how it's going to perform and how we can modify our process with this new tool in the toolkit. The project budget is about $8 million. It hasn't really moved much. We had a couple of extra change orders on the site prep. It's, noise, a couple of percent. But in general, we're at that $8 million investment. We're very happy to say and thankful to Congressman Lou Correa for partnering with us after the fact. He earmarked some funds toward us for a little less than $3.5 million to help offset. But OC San is so interested in making sure we have a way forward that we're willing to invest this money and show the industry that supercritical water oxidation has promise and could be a part of the way we all move forward. Certainly, OC San is looking at it as a way for us to move forward with all the constraints that are coming on biosolids and methane production. The site has been prepped. We're ready to go pretty much. We're waiting for the units to be delivered. 374 Water, I talk with them about every 2 weeks now. They are in the process of doing their commissioning tests. They're making a couple of modifications based on their latest learnings, but we anticipate in mid-March they should be moving toward their factory acceptance testing, where they run it for 48 hours at its designed capacity. We anticipate them shipping the unit to us in May and getting it put down and started up in July, August. They will run it for 6 months. Then we will run it for 6 months. That way we know that it's not smoke and mirrors. We will be able to attest that it is a viable industrial machine, that it will work. I have no doubt that serial number 1, and I've said this many times, will look different than serial number 2. If it doesn't, then we're either incredibly lucky and guessing at things, or we haven't learned enough. So I think the first few serial numbers will get better and more capable. Our job is to make sure serial number 1 is a viable machine, and all the improvements that follow on just make it even more effective, efficient, and reliable. Our hope is in the long term that we will be able to demonstrate that 6 tons a day machine. We will then start to investigate building a 30-ton a day unit. We will verify what compound destruction we're seeing in the 6-ton unit. We'll look at all the air, off-gassing air streams, and really make sure we understand what's going in and what's coming out and what the machine is capable of doing. And once we get the 30-ton proven, our hope is to create a 200-ton a day unit, and then that would be the ultimate size for us. where we would have multiple trains. Again, I told you we get 500 tons a day of biosolids, but based on the destruction that happens in the digesters, you would have to think that we're closer to 1,300 tons a day of raw sludge. So if we wanted to go to complete destruction of all of our sludge and conversion to electricity and heat, it would take multiple 200 ton a day units. I continue to be a fan of the SCWO technology. As I first heard of it in coordination with chemical weapons disposal. So I know that it works. I know that it will destroy some pretty nasty compounds. So things like leachate from landfills, food waste, ion exchange resin is a really interesting opportunity, I think, for the water district and others that are in the water side of the world, and other constituents of concern that are going to be identified. I think there are lots of opportunities for us to apply this new machine once we get it up and running. So I know there were some questions about how does SCWO relate to advanced oxidation. And I think they're kind of apples and oranges. I think for OC San, with our solids and biosolids, this is more the direction we need to work with, because our constituents of concern are going to stick to our biosolids, they're going to stick to our solids. So that kind of technology is very, very different than advanced oxidation with peroxides and catalysts and UV light, those sorts of things. It would take so much light, it would take so much peroxide to deal with our solids that it's just an apples and oranges comparison. So I know there are a couple of questions about that, but it's really two different animals. This is really about concentrating things like, again, ion exchange resin or sludge biosolids versus very clean water, which has a whole different step. So this isn't a viable technology to deal with RO concentrate. But if you were to run your RO concentrate through ion exchange and then destroy the resin through this, that might be a way it comes together. So again, where I think we're going as an industry on the wastewater side is that we must find a way to concentrate and destroy. Moving contaminants around, displacing them, separating them isn't going to get us anywhere. We can't rearrange the deck chairs. We need to find a way to concentrate and destroy in the long term. That's what OC San's looking for. That's what we're committed to trying to find. And that's why we're willing to invest $8 million to prove it. Please follow us. We have great social media. We're doing our best to keep the industry moving forward. Lots of resources here online for you to follow. And with that, I am happy to answer any questions you may have.
Awesome. Thank you so much, Rob. And you have, it's your 70th anniversary, which we see on the slide as well. So congratulations on 70 years of innovation. And this is a great example of pushing that needle even more forward. So thank you, Rob, for that great presentation. I already see questions from the audience popping up, so I think we can go ahead and tackle them. But I wanted to mention for anyone else that has questions, please type them away in the Q&A box. We'll try to get to as many questions as we can today. And if not, please, or if you think of something afterwards, please email us at info@ocwd.com. And we'll make sure, yes, that goes to the Orange County Water District, but we will route that question over to our great friends and partners at OC San for any follow-up information. So,
would you like me to start at the top of the Q&A and work down?
Sure, Rob. Yeah, and you know what? Some of them I see kind of speak to similar topics. So maybe what I could do, Rob, is just
Please.
Categorize them for us too. I do have some questions, for example, on the timeline. Maybe we could jump into that. You showed that great slide of the project delivery. One question is about, what kind of, how did we get pushed back into the, or kind of why did the delivery get pushed back to May? And another question is about the demonstration pilot project, and is there something, is there a potential for a full-scale project later on, which I think you did touch on in terms of the 200 tons a day, but if you would like to elaborate on those.
So why did we get pushed back? I would say that when you're doing the first of anything, it's a really hard thing to design a machine. I look at, as an example, what Elon Musk goes through when he's trying to figure out how to launch a rocket or build one of his Tesla cars. It takes a bit of effort to get there. You build your pilot, you learn some lessons, you make the tweak changes, and you keep moving forward. I think 374 Water has been going through that natural evolution process. I can tell you from my experience, we put in centrifuge facilities at both of our treatment plants in the last 5 years. And it took us 3 years to really take what is a mature technology that's been around for 50 years, centrifuge technology, and really optimize it and get to the point where we make 25% sludge day in and day out. It's not easy to deal with sludge. It's not easy to have an optimized industrial machine. So the reason I think there's been a delay of about a year or year and a half is 374 has put in the work to deliver a machine that is resilient. I admonish them, to be honest and totally forthright, to say, do not deliver me a machine that isn't going to work as an industrial machine. Take your time and get it right. We want this thing to be effective. You have all the resources there in Indiana. Build it, test it, break it, build it again. This is my admonishment to them. But get the machine right. Get your sludge pumps right. Get your air compressors right. Get your sludge handling equipment right. Learn, optimize your control system, and that just takes time and iteration. And they are making marvelous progress. The things that I worried about with this technology, salt plugging and some of the other things that have been the death of prior attempts at supercritical water oxidation, they seem to have defeated. So I'm very bullish, very, very happy with their progress. What was the second part of that question?
Will there be a full-scale demonstration project?
So our plan is to nail this 6-ton unit, show it works, make the next unit a 30-ton unit. That's sort of the natural step size when you look at their pipe reactor growth opportunity. And that 30-ton unit then has the scale to show energy recovery. The 6-ton-a-day unit, it doesn't really pencil out. You don't get enough energy back to really pay for the work and effort to have a small steam expander on the end. They'll probably get there someday, but I didn't want to wait for that. So the next step is 30 tons. When we demonstrate that with energy recovery, probably just steam to our existing steam turbine, then we'll work on the 200-ton-day unit. It gets really exciting when you start thinking about how those numbers add up and the number of BTUs per cubic foot of biosolids. You're talking hundreds of megawatts in electrical capacity potentially if this becomes the way we deal with raw sludge. And again, that's not a foregone conclusion. We have to go through the learning process and figure out where it's going to go. But the scale up is 6, 30, 200, and then multiple trains of 200 for OC San.
Thank you, Rob. I've got a handful of questions related to cost and energy consumption that I thought we could tackle together. Do you have a sense of, is there a difference in costs based on what maybe a current process is versus the supercritical water oxidation process, or what are those costs? And then if you could talk a little bit about energy consumption as well.
I have been very hesitant to make any kind of representations about cost because we have all worked in the machine development world or new technology development. I want to wait till this thing is ready. The first step is, will it work? The second step for me is, okay, then how much is it going to cost when it's actually operating as it should operate? You can make all sorts of pie in the sky guesses and estimates, but I would never want to tell anybody that I feel confident that it's going to be one number or another. Directionally, I believe it's going to be cheaper to operate overall than a classic digestion with all of its mixing and energy costs and heating, and sludge dewatering or thickening, which we have here, and truck loading and hauling and reuse of biosolids off-site. I think there's a lot of opportunity for this to be much more effective and efficient. I think it's got a much smaller environmental footprint because I'm not running 25 diesel trucks from Fountain Valley to Arizona or Fountain Valley to the Central Valley. I reduced that volume of trucking by a factor of 20. So maybe a truck and a half, and that truck and a half is going to have that sandy, silty, high phosphorus, high iron amendment that I could use anywhere, whether it's a golf course, I think, a park, potentially. Worst case, putting it in the landfill because it's just sand at that point. It's not organic anymore. That would be the worst outcome, but that's still a much easier thing to do with electric trucks in the future. It's got a much smaller footprint. So it's more than just dollars and cents for us. It's really about all these future regulations making what we do more and more difficult and less sustainable for us.
And thank you, Rob. And Rob, I do see now, I'm seeing a handful of questions coming in, and I think you see them as well in the Q&A box. If you're up for it, I would like to take you up on your offer to maybe kind of tackle the questions as you see them coming in, because they are, I think that might help us address the most amount of questions in the time that we have. Is that something you're comfortable doing?
I will give it my best shot. So what does the fluorine mass balance perform to confirm that PFAS before were not transformed to another PFAS? I would point you toward the ASCE articles that were done. I believe there's a person online, I think I saw from 374 Water. If you could put that link in the chat, it would save me the effort. But a lot of work has gone into, is supercritical just reforming, or is it actually destroying down to salts? ASCE looked at 3 units, Battelle, 374 Water, and General Atomics, and came to the conclusion that it was destroyed down to basically the calcium fluoride. That's my understanding. So next is fascinating and promising projects. Will ARG be destroyed as well? Not sure what ARG is, to be honest. I've been vested, so I apologize. If you could add it to the bottom, I'll try and get to it once I know what an ARG is. Assuming you are able to demonstrate effectiveness of pilot unit, if you plan to implement SCWO at full scale, do you envision SCWO replacing the entirety of your solids handling? I don't have an expectation yet. I think SCWO is such an interesting tool. It may have several ways to fit. We are in the process of building new digesters here at plant number 2. I think that SCWO can be a very complementary piece to having digesters. It's always nice to have a big tank buffer. We already have engines and the infrastructure in place to deal with biosolids and gas conversion to energy and heat. So there's a lot of ways going forward that we could slow roll as our investments come up for renewal, meaning when a digester reaches end of life, maybe we don't replace digesters. But in the short to medium term, I'm not ready to say that SCWO we're diving in with both feet and we'll never build a digester again. I think the two can be complementary. I think the SCWO can act as a heat source to heat up the sludge to a digester, saving digester gas consumption for heating, especially in the winter months. So there's a lot of ways SCWO could be put into the process. And maybe we just find our highest PFAS sludge streams or our highest microplastic sludge streams and destroy those to start with. So there's a lot of ways SCWO can be slow rolled in while we learn and adjust. Next one, okay, going on the fly here. SCWO may prove to be the black box solution for PFAS destruction in biosolids. How does OC plan to address PFAS in liquid process with RO at GWRS? What about RO rejection stream? That is a great long-term question. I believe the water district is doing some investigation in that. That's where I would look for them to take the lead. As a wastewater agency, my line would be that falls on the water side, and we'll work together to find the least cost solution to the long-term problem of PFAS that resides. I think when you're talking ocean effluent, I don't think you're talking the same sort of problem. And this is a dicey thing for me to even begin to talk about because I know the Regional Water Quality Control Board's on the line. But in general, safe disposal to the ocean is one way to go. What that level is, I'm sure we will be adjusting over a period of years in the future. So resin may or may not work. That resin, I think, can certainly be destroyed in a supercritical unit, whether it's 374's unit or General Atomics unit out of San Diego. I think both of them would do a great job of that.
Thank you, Rob. And I just wanted to jump in. I do see a handful of questions related to the water side of things, and we'll get back to those questions in more detail as we have it. So thank you. Maybe we could punt a couple questions back to you on the wastewater side of things. You had mentioned an air, I think air quality permit. Have you received that permit? And can you talk a little bit about that? How arduous was the permitting process is the question for you.
We enjoy being a part of the South Coast Air Quality Management District and fully support all the processes they do to provide safe and healthy air. And that does involve an arduous process. And yes, we do have a permit. We're thankful for their cooperative and collaborative effort because we know it's new and different. And new and different is always more challenging to make sure we've thought of all the what ifs to make sure we aren't putting something in the air for the residents in the area or our own workers to deal with. So it was arduous, it was worth it, and we have our permit and we are ready for the unit to be delivered. What is the residence time for sludge in the SCWO reactor? The answer is seconds, less than 10, I think is the safe answer. It's a very fast reaction when you're working it out. Good mixing makes for good fast reactions. As soon as it's supercritical, it does its thing. Time frame associated with SCWO treatment from start to finish. It is a continuous operation, and again, it's very quick from start to finish. It's probably less than a minute. You're just allowing time for things to exchange heat. The actual reaction takes place literally in seconds. Great presentation. Okay, I'll move on. No, just kidding. How would integration of SCWO affect main treatment process or GWRS? Again, it gets down to how we choose to implement it, and the two plants are different. I think from an industry perspective, I think there's endless possibilities what different plants with different infrastructure might do with SCWO. That's what makes it so exciting. Anything you can concentrate to the side stream question is a great opportunity for SCWO to do its thing. Those solids become the fuel. The problematic compounds are just collateral damage, which is a great way to get rid of them. How large is the footprint of a 6-ton unit? It's one shipping container. Now we have 2 shipping containers because the first unit is really the sludge pre-processing. So yes, I would count that, but we did upsize that so it would be capable of dealing with a 30-ton unit. the 30-ton unit is expected to be 3 shipping containers. So 8 feet wide, 40 feet long, 8 feet high, the standard shipping container. So much smaller footprint versus digestion, centrifuge facilities, heaters, all the things that go with running a digestion complex. SCWO answered that one, I think. What kind of operational challenges are you expecting, and how are you preparing your staff for them? The way we're going to prepare for them is the vendor will be on site and run the unit for the first 6 months, and our staff will be there shoulder to shoulder learning for the first 6 months. It is a highly automated process. So even when you go watch it, it is as exciting as watching paint dry, because black stuff goes in and clear air comes out, and water with some minerals come out the side. There's really nothing to see. So it's all on the computer screens. It's all automated. So it's really kind of anticlimactic from that point of view. It's a little like taking the GWRS tour and OC sand tour. I show you the bar screens up front. You see that black water coming in. Yeah, we can show you a couple of places where the water daylights, but at the end you get a cup of water. So it's the same idea. Your inputs go in and your clean outputs come out. And no, I will not be drinking the water that leaves the SCWO unit. I know somebody's going to ask.
Rob, I just wanted to do a quick time check as well. We're about to 12:59. Rob has so kindly agreed to stay on for a couple minutes longer to address as many questions as we can today. But please know we'll likely be following up with any outstanding questions if we're not able to get to them. And I did want to note that Sunny so kindly did provide the link to the AFDE library document that you were referencing, so folks can click on that for more information as well. Rob, I do see some questions about will you be tracking or measuring the PFAS in and going out, and how will you do that?
We have a thorough program of sampling for all the air pollutant criteria measures, PFAS in and out. That is the point of running the demonstration, to verify that the 6-ton industrial unit meets all of the same performance requirements that we saw in the 1-ton unit that was so promising at Duke University. There will be a very extensive program of influent and effluent sampling, both air and water. So yeah, it's extensive, too much to talk about now.
And back to an energy question, how do the energy requirements from SCWO compare to incineration?
The beautiful part of this process is it's not energy intensive. The air compressor is part of your load, and the sludge compressor is part of your load, but you're also picking that back up. You're recovering it out the back end when you're in your heat recovery mode, similar to running a turbine. Once this thing gets running, it's self-generating. It's using the heat of the fuel being the biosolids. So it's going to be net energy positive at scale. For this little 6-ton unit, if I remember right, there's an electrical load of like 10 kW, maybe 30 kW. It's a small lighting panel, so it's not a big load. It's using the energy that exists in the material itself for heat and long-term power.
Can you talk a little bit more about the regulatory requirements for PFAS disposal? So we recognize in the water industry, we have to treat water for PFAS. Interested to hear a little bit more. You've touched on it a little bit, Rob, but I don't know if you have any additional comments or.
It is certainly heating up on our side of the world. As I said, there's a lawsuit that's hit all the industry publications in the last week or two, where some farmers, ranchers in Texas are suing Synagro. The first of what, if you read the articles, it's a flood of anticipated litigation regarding biosolids application, and it's going to heat up, I'm afraid, far too quickly because it's too easy for our environmental groups to say what they don't want. The problem is we really don't have a good answer as an industry for where to go. That's why we started this so long ago. We realized it's going to take time, but the wastewater side's really being pushed primarily at the biosolids position now. It's just a question of time until effluents and other things are asked about. So providing an answer in some way and having a way forward is very important to OC San.
Thank you, Rob. And I'm going to end on this question here. And again, I know that there are some outstanding questions. We'll be sure to get back to folks. Are there any concerns regarding unforeseeable toxic byproducts being produced as a result of the treatment process?
In my mind, no. It's always a risk, obviously, but you're talking about a technology that has been used for chemical weapons disposal. And if you can put VX gas, mustard gas through this thing, it has been tested again with AFFF, which is pure firefighting foam. It's been tested with some pretty nasty things by 374 and others. So I think the promise of the physics, it's not even technology at that point. The promise of the physics is it does a really good job of breaking all of those chemical bonds, whether they're carbon bonds, fluorine bonds, hydrogen bonds. It just, at that temperature and pressure, breaks them down. The energy is released and they reform at their lowest state in benign products like N2, nitrogen, carbon dioxide, water, and salts. So can it happen? Of course. Are we going to sample for it? Of course. Do I think the risk is high? I do not.
Awesome. Well, Rob, thank you so much. This has been a great presentation, as evidenced by the many questions we got today. So we're really excited to have you on here, have OC San, our wastewater partners, talk about this innovative technology and then what you're doing. And we're excited to see the project progress and hear more about it in the future. So Rob, thank you so much for your time today. Really appreciate it. And thank you for sticking on a couple minutes longer as well to answer these questions. And I also want to thank all our attendees for joining us today and for also sticking around past the hour to hear this and get your questions answered. So we will be in touch after the webinar as well. And we hope you enjoyed today. And last reminder that this webinar is recorded and will be available on OCWD's YouTube channel. And with that, I think we shall conclude. Thank you again, Rob, and thank you,
Thank you
everyone.
all. Appreciate it. Thank you.
Have a great day. Bye, everyone.